is a review of atomic structure covering defining an atom, structure of a nuclear atom, and distinguishing among atoms. I will also cover a little bit about nuclear radiation. What is an atom? An atom is the smallest particle of an element. Within an atom, there are three types of subatomic particles: the proton, neutron, and electron. The proton is a positively charged subatomic particle. Neutron has no charge, so it's neutral. An electron is negative, so it's negatively charged. In this picture, as you can see that there's three protons, so it would be lithium. Who discovered the subatomic particles? The proton was discovered in 1911 by Goldstein. The neutron was discovered in 1932 by Chadwick, and the electron was discovered in 1897 by J.J. Thomson using the cathode ray. In 1904, J.J. Thomson created the first model of an atom, known as the plum pudding model. As you can see in this picture, Thomson believed that electrons, or the so-called plums, are in a sphere of positive pudding. Today we know that this model is inaccurate, but at the time it was revolutionary. Democritus reasoned that atoms are indivisible and indestructible. Dalton's atomic theory. 1. All elements are made of atoms. 2. Atoms of the same element are identical, and atoms of different elements are different. 3. Different atoms can physically mix or chemically combine. Compounds. 4. Chemical reactions occur when atoms join, separate, or rearrange. Elements are different because they contain different numbers of protons. An atomic number is the number of protons in an atom. Mass number is the total number of protons and neutrons in an atom. Atomic number is important because it distinguishes different types of elements from each other. To find the number of neutrons in an atom, you take the mass number and subtract the atomic number. An atom is neutral when protons equal electrons, meaning there is no charge. So sometimes you'll find elements written like this. For this example, I'm using gold, and its symbol, as you can see here, is AU, and its mass number is written up here to the top left of it, and it's 197, and then the atomic number is below the mass number, which is 79. Okay, so isotopes are atoms that have the same number of protons but different number of neutrons, meaning it's like the same atom, but they have slightly different masses because of the number of neutrons. For atomic mass unit, or AMU, one proton weighs 1 AMU and one electron weighs 1 AMU, and they're used for like the unit for atomic mass. So after you calculate the atomic mass, you use this as the unit. For percent abundance, it's how common one isotope is to another isotope, and atomic mass is the weighted average mass of an element. What you'll find with percent abundance is traditionally one isotope will be more common than the other. Calculate the atomic mass of an element, multiply the mass of each isotope by its natural abundance expressed as a decimal, and then add the products. For this example, we'll use carbon. Carbon-12 is found 98.89% naturally, and carbon-13 is found 1.11% naturally. These here are the percent abundances of each isotope. Okay, so here's the information that we started with again, and to find the atomic mass of carbon, you take the mass from the first isotope and you multiply it by its natural abundance in decimal form. So you take 12 times 0.9889, and then you add it to the other isotope multiplied by its percentage, so 13 times 0.0111, and then you just add the products, and then you get 12.011 AMU, so carbon's atomic mass is 12. What is nuclear radiation? Radioactivity is the spontaneous emission of rays. Nuclear radiation are the rays emitted from a radioactive source. A radioisotope. Nuclear reactions begin with unstable isotopes. There are three types of nuclear reactions: alpha, beta, and gamma. So this is an example of an alpha reaction. And so here we start with 238 over 92U, and then we have radioactive decay, and then it releases an alpha particle, which is 4 over 2He, and then plus 234 plus 90TH. And with these types of problems, you must remember the law of conservation of mass, and you must make sure that the numbers on the top add up and then the numbers on the bottom add up. See, we have 238 is 234 plus 4, so that's right, and then 92 is 90 plus 2, so this is right. Next we have our beta reaction, and this one's a little different because we have 14 over 6C in radioactive decay, then we get 14 over 7N because our beta particle has a 0 on the top, so the mass number stays the same, and then 7 plus -1 equals 6. So this one can be a little tricky, but you just have to remember the law of conservation of mass. And then our gamma reaction, we have 234 over 90TH, and then after radioactive decay, it's 230 over 88Ra, plus an alpha particle, which is 4 over 2He, plus a gamma particle, and the gamma particle doesn't have any effect to the numbers, but you just have to know that it's there.